Okay, today class we're going to be talking about ultrasonic inspection, and primarily in the 0 degree longitudinal mode, where we use for thickness measurement and finding defects such as corrosion and that type of thing. And the primary instrument we're going to use is the piezoelectric transducer, which is this transducer. This face right here is the surface we want to interact with the part. And for our test today, we're going to use an ultrasonic instrument and an oscilloscope. An oscilloscope, if you have not used an oscilloscope, is a trace of amplitude versus time. And remember, we talked about the A scan as being amplitude versus time. So the first thing I think you want to notice is we have a block, and we have it looks like a good block. I've got some things taped off here so that you can't see what's in it, and we're going to try to investigate what's in it, and then we're going to take some measurements to find out if there is anything in it, how deep it is, okay? And the first thing we want to notice is that when I put my transducer to work, I should be able to see a signal over here. This is called the initial pulse, and that allows us to activate the transducer. And you'll notice the first thing I do is put it on the part, and I shouldn't see anything. I really don't see anything signal wise, and that's because I need a couplant. Remember, a couplant is a liquid, so I've got a little oil here, and I want to spread it on the part. Okay, the first thing you should see is I have a really nice signal. Okay, so this signal right here is from the part, and I'm only able to get that because I've now coupled the transducer to the part. So again, if you have a sonogram, remember the gel they put on your body, that was to allow the sound to get in your body. So the same thing is here. So right now I'm taking a measurement of what's in this block, and so right now the wave is going through the part and coming back. And a key function of what we want to do in this experiment is to discuss the measurement of how we determine thickness. And if I can get my faithful assistant here, velocity usually is distance divided by time, and in this case we're going to be doing a pulse echo, so we're going to go down and back, so that's twice the distance divided by time. So the velocity in our material is going to be 2 times the thickness of the part divided by the time we measure on the oscilloscope. And earlier I measured the thickness of the block I'm doing, and it may be hard to see, but it's basically 3/4 of an inch in thickness. Alright, so if we use that equation, then I should have 0.75 inches times 2 divided by the measurement of time we measure, and that should give me the velocity of ultrasound in this part. And this part is an aluminum part. So if I measure this, and if I can get my assistant to go over there and focus in on this screen, you should see that the major division is 1 microsecond. And so from this edge to that signal is 6 microseconds. So if I take that equation, 0.75 times 2 divided by 6e to the minus 6 seconds, I get a velocity of 2.5 times 10 to the 5th inches per second. And that's the standard velocity for ultrasound in aluminum. Okay, now I'm going to do a slightly different test right quick. So one of the things I'd like you to do as part of the lab is, as we look at the back page, second to the last page, we should have a table that looks something like that. So for the aluminum, okay, and we'll take some tests in a minute, but I'd like you to have step thickness or part thickness, measured time, and then calculated velocity. Okay, and we're going to be doing some various renditions of this. So on that block, the first thing you should do is we have a 3/4 inch thick part, and our time measurement was 6 times 10 to the minus 6 seconds. So if I use that equation, velocity is equal to 2 times the thickness of the part divided by the time, then I come out with 2.5 times 10 to the 5th inches per microsecond. Okay? So now we're going to use this a little bit differently. I don't have an aluminum step wedge, so I'd like to kind of trace through this part right quick with my ultrasound, just as if you were looking at a pipe wall. Okay, so I'm going to pass along this part, and all of a sudden I think you will see an extra signal over here. Oops, excuse me. Okay, so the question might be, what is that? And we'll talk about that in a minute. Okay, and as I keep going along the part, I see another signal come up. So either that means there's something in that block that is before the back of the wall of the block, and we're going to do some calculations with that, and I want to help you fill out your table. And there's another one. There's another one. So what I'd like to do on your table is, instead of having a step wedge known thickness, what I want to do is say, okay, the first data set that I have is for a signal that occurs at 5 microseconds. So on your table, measured time, put 5 microseconds. And since we've already calculated the velocity in aluminum, so on the third column, instead of calculated velocity, put there the actual velocity that we've got is 2.5 times 10 to the 5th inches per second. And we're going to use that now to measure how deep is this signal relative to the front surface. So if I was trying to find a defect below the surface, it will tell me that there is a defect that's 5 microseconds down. And if I do the calculation, okay, and I do the distance is equal to velocity times time divided by 2. So I've got time is 5. Well, I'm going to use the velocity, 2.5 times 10 to the minus 10 to the 5th inches per second divided by 5. Excuse me, I had that wrong. Never mind. Okay. Okay, 2.5 e to the 5th times the measured time, which is 5 e to the minus 6 seconds. And then I divide that by 2. That tells me that that signal is actually 5.625 inches below the surface, and we'll look at that in just a second. So in your first table, okay, we're going to have 5 microseconds, or 5 times 10 to the minus 6 seconds. Our velocity is 2 times 10 to the 5th inches per second. And if I do the equation of velocity is equal to 2d divided by time, and use that to solve for the thickness from the top surface, you'll find that it should be 0.625. Okay, now let's keep doing that on this block because it's got several defects in it. Okay, so here's another defect, and that defect is basically a 4.25 microseconds below the surface. So write down 4.25. And then we'll find another one over here. Let's see, let me just make sure I got that one done right. Sometimes the cup one evaporates. Alright, so that one's 4.25, okay. And there's one that's about 3.5, and there's one that's about 2.7. Okay, so if we write those numbers down, so let's write those numbers down again. Okay, we've got this one at basically 5. We've got another one that's at 4.25, 4.3 or so. We have another one that's over here at 3.5, We have another one over here that's about 2.7. Okay, and if we do those calculations, you should be getting depths to those defects. And if you look at this part here, I've taken the tape off of it, and our first one that we looked at is actually this one. I've turned it around 180 degrees, so this one is actually, we calculated 625 below the surface, and if I measure that, it's basically 5/8 of an inch below the surface, which is 0.625. So now you've become an ultrasonic inspector. Okay, so the next ones you should get, we got a 1/2 inch below the surface, and then we got, excuse me, that one's a little bit less than a 1/2 inch. It's about what's that? 8 to 9, 10/16. There's a 1/2 inch, and then there's 3/8. Okay. All right, so we can calculate those things and see what that is. Now that's all using the 0 degree, and remember we can't couple a sound unless we have a couplet. All right, so that again shows me a signal here. Okay, now I'm going to turn this block over on the side, and that block should be 2 inches wide. Okay, so I don't think I need to change my scope so I can see the signal timing on the scope. Oops, hang on just a second, let me get that done here. Hang on. I'm bringing the back wall to 0. Okay, so now if I put this over here, and right now if you can see this, I've got 5 microseconds per division. So the first signal I see is now 1, 2, 3, so it's 15, about 16 microseconds. So I know the velocity, and I want to calculate the thickness, then that basically is okay. All right, so if I have that, let's see, let me do a quick calculation. Okay, so we got I'm going to use this equation. I'm going to try to calculate what the distance or thickness is. So I've got velocity 2.5 e to the 5th times 16 e to the minus 6 divided by 2. And wait a minute, I still didn't do the right calculation. I'm sorry. 2.5 e to the 5th times e to the minus 6 equals divided by 2. Okay, I get 2 inches, which is what I expected to get. Okay, so now I'm looking at this signal over here. That's 2 inches. So you can see how the thickness and potential corrosion could be found. Okay, now I have another block, which is steel, and this has a step wedge with known thicknesses. This is a 1/2 inch, 0.4, 0.3, 0.2, 0.1 inch thick. It's steel, and one of the things you're going to see, I think, pretty quickly is I had this as aluminum, and let me get back over on the thin scale. All right. Okay, so previously we had the aluminum to be about 0.6, and the first thing you're going to notice is that this is 0.75 inches thick, and so we're going to go to the 1/2 inch thick steel, so it should be closer. All right, and it is. and the amplitude's quite a bit down basically from the aluminum. Aluminum is easier to get sound in. Okay, so in this case, our 1/2 inch thick gives us a timing of right at 4 microseconds. Okay, so if you're on your table now and we put measured time, let's go 4 microseconds, and I know the thickness of the step wedge is 0.5 inches. So if I do that calculation, twice times 0.5 divided by 4 microseconds, e to the -6. Okay, and that gives me 2.5, and that's a little bit off. Okay, so let's see what I want to do here. So that's 0.5 times 2 divided by Alright, let's see if I've got this set right. Okay, that's okay. So it's actually 1 divided by okay, so that comes out to be 2.38, so that's closer. Okay, and again, if I do this, I get about 3.3. This gives me about 2.4, and this is almost unreadable because it's in the back wall here, so that means I can't really use that value. So on your table, put in 0.5 for the thickness of the block, and this will be a steel step wedge, and the time that we have is 4.25 or maybe 4.2, and then for a 0.4 inch thick steel block we have 3.4, and for the 0.4 inch 0.3 inch steel block we have 2.6 or so, and then calculate the velocities, if you will, using that equation. Okay, now we're going to go back to our other block, and we talked about the different types of visualization scans. We've got A scan, which is, again, the A scan is this scan right here. So we're actually looking at amplitude versus time. This is time, and this is amplitude. Okay, so we can see that. Now if I were to have a scanner device that kept track of where I am, okay, and I scan this whole block, I would see regions where I'm getting a signal, like right there. Okay, and so if I scanned that and took my position and the amplitude, what I would notice is I would get a line all the way across the block at this depth. So I would have a C-scan from the top view that would show a top plate with no defects, and all of a sudden I would have a defect here, and then I would have a defect here that would go across the block. So if I look at my potential C-scan, hang on, I'll draw something. Okay. So if I did my C-scan, I would notice that I have no indications here, and all of a sudden I have an indication here, which is right here. And so I would get a line across there, and then if I moved it over, I'd get a line across there, a line across there. And so this is called the C-scan, as we've talked about. Okay? So I would have a top aerial view of my block, and as I scanned it, I noticed there were signals below the surface. And now that I put that together with my raster scan, which is going back and forth, and I'm just plotting the amplitude as a function of position, then I would notice that I would see these four areas there that are closer to my transducer than the back wall of the part. Okay, so I would know there's something in there that was a defect. So if I had a corrosion area, area that had been corroded away, this would be a simulated corrosion. And also all of a sudden on my pipe wall, for example, if I had areas of corroded regions, I would know those are like those stripes, okay? And those are some actual types of corrosion called tiger striping that occurs in some piping because of the flow. So you might see something like that. Usually, you might, hang on just a second. Usually if you have a corrosion pit, you're going to see more of a spot in your C-scan, so that will show that type of thing. And again, that's due to the fact that when we do our scan, going back and forth with our 0-degree transducer, I might see a signal like that from the corrosion spot. And as I go away from it, it goes away. If I go toward it again, it comes up. And if I keep track again of my amplitude as I plot back and forth, I get to make this image, which is called a C-scan image. Okay, any questions? So what we've learned today is we got to have a transducer. It looks like that. We're using it in 0-degree mode. To make it work, we have to have a couplant, which is a liquid, usually oil or glycerin or water even. And we have to have an ultrasonic instrument and an oscilloscope. And today, with the devices that are used primarily for measuring 0-degree thickness, this is all put together in one instrument that's about the size maybe of a calculator these days, so it's pretty small. And I just don't have that for the lab. Okay? Thank you.
What about the surface? What about the surface that it's on? Does it?
Oh, this isn't going through there.
So it doesn't go all the way through?
No, because it's not coupled.
I see.
That was a question of a student of mine. So her question was, the fact that it was sitting on this part, why isn't it going into the instrument? If it were coupled, it would, but it's not coupled, so it's not going to go into that area there. Okay?